Okay. Okay, thank you.
Okay, so good afternoon, everyone. So I think we're going to start the session now. Great. So I would like to welcome our first speaker. So Chui Hao Zhang from the University of Hong Kong.
Yeah.
And he's going to tell us about SPH modeling of soil.
Okay, thank you. Good afternoon. I'm Chui Hao Zhang from University of Hong Kong. And today I'm going to talk about SPH modeling of soil hydrophobicity. I will introduce my topic from the following 4 parts. Okay, first I will talk about the background. Soil hydrophobicity is defined as a reduction of affinity between soil particles and water. And the hydrophobic properties of soils have been firstly investigated in California soils. And during 1990s, soil hydrophobicity was extensively reported, arousing people's attention to this problem. And persistent finding on this phenomenon indicated that soil hydrophobicity do not occur in isolation, but widespread all over the world. Early studies mainly focused on natural generated hydrophobic soils, such as by wildfires. So we know that some oily materials will be produced after burning plants. So these oily materials can make soils hydrophobic. And soil hydrophobicity was generally considered as negative in soil processes because it is considered that soil hydrophobicity is considered as an aggregating factor for some natural disasters, such as soil erosion and debris flows. However, in recent years, researchers began to consider taking advantage of soil hydrophobicity to benefit mankind. So based on synthetically induced hydrophobic soils, its hydraulic and mechanical behaviors are studied. And it is expected that these hydrophobic soils can be applied in ground infrastructure to delay or restrict water infiltration and thus prevent their failure and long-term degradation. Okay, then I guess just now Professor Halim have introduced about this contact angle and hydrophobicity in detail. So I will just go through this briefly. And we use contact angle to characterize the soil hydrophobicity. And also the contact angle in a smooth surface is called the intrinsic contact angle. And the contact angle in a rough surface is called the apparent contact angle. And in laboratory, we can measure the contact angle based on the sensor drop method. And also if fluid infiltrate into the gaps of the substrate, then we call this window state. Otherwise, it's called the Casey state. And previously, people have did many experiments to study the effect of soil hydrophobicity on soil properties. Such as in this study, they use the water droplet to hit the soil surface, to hit the soils, and the soils can be hydrophilic or hydrophobic. And from the results, we can see that if the soils are hydrophobic, there are much more soil particles that are being splashed. This can actually explain why soils can aggregate some natural disasters such as debris flows or soil erosion. And in this study, they use a flume test to investigate the effect of hydrophobicity on real erosion. And from the results, we can see that we can see that if the gray color in the red corner, the gray color what repellent soils or hydrophobic soils. We can see that if the soils are hydrophobic, then the total mass of sediment are much larger than the wettable soils. And then, in this study, they investigated the effect of hydrophobicity on debris flow entrainment. And also from this figure, we can see that the erosion rate increases with increasing contact angle, which is hydrophobicity. And previously, these are mainly experimental studies. And in this study, I'm going to use numerical methods. And for numerical aspects, there are also many previous studies. Like firstly, for volume of fluid or smooth particle hydrodynamics, they can model the movement of a droplet on a smooth surface or the infiltration of the droplet into porous media. and also for the lattice Boltzmann method or material point method. And I summarize, and from the previous studies, I found there's still some gaps between what I want to do and what have been done. The first thing is that previous research mainly focused on a droplet with hydrophobic smooth surfaces or idealized granular surfaces. But for me, since I need to model soils and soil particles are irregular, so further work is needed on realistic soil particle shapes. And also, the solid particles are generally fixed in the previous studies. Therefore, incorporating the movement of solid particles is necessary so that we can model urinal process of soils, including other phenomena in geotechnical engineering and earth surface processes. And here I summarize the pros and cons of different numerical methods. And I just summarize this from the literatures. And I know people here focus on different methods. And if I'm not rigorous here, you may just correct me. And finally, we decided to choose SPH because it's advantage in modeling complex interface shapes. And previously, we have some studies based on smooth particle hydrodynamics, but these are mainly on solid aspects, elasticity and plasticity. But in this study, we are going to introduce the influence of water, and we need to consider the contact angle, the surface tension, and the soil hydrophobicity. And okay, I will introduce SPH briefly. In SPH, we use a set of particles to discrete the continuum domain. And also we think that the physical quantities are carried by each particle. And also the physical quantity of a particle I, is related to its neighbor particles, like particle J. And this relation can be described by a function called the kernel function. And then these are the Gaussian equations and especially discretizations for this for the fluids and solids. And we developed our codes based on this open source, especially library called Sphinxes. Okay, first thing is that we need to model surface tension. Here we use the continuous surface force model, so continuous surface force method. And in this method, we label different fluids with different colors. This is called the color function. And also the sharp interface is treated as a transition zone. And also we use this equation to calculate the surface tension force. Here the sigma is the surface tension coefficient and the C is the color function, can be calculated based on this equation. And these are some basic verification to verify the stability of our method. The first one is a square droplet becomes sphere on the surface tension. And also the second one is the fusion of two droplets. You can see that they will just to verify stability of our numerical methods. And the bottom is just the three-dimensional situation. We can see the sphere become the cube become a sphere, and also the fusion of two three-dimensional 3D droplets. And the next step is we need to introduce contact angle model. The first one we tried is called the imposing contact angle, which means that we define a contact angle before the simulation, and then during the simulation we check the current contact angle at each time step. And if the current contact angle is not the same with the preset contact angle, we just give extra force to let the droplet deform towards the preset contact angle. And it's okay, we can see that from we can see the droplet and also the sliding of a droplet in a hydrophobic surface, or the droplet on the granular surface. We can see it's okay to simulate some surface processes from this model, but we found that if we want to simulate the infiltration process, it's not so good, because we know that if the contact angle less than 90 degrees, let's say 60 degrees, we actually think we think it's hydrophilic. But if we use this model, the contact angle then the contact angle has to be 60 degrees. It cannot infiltrate into the porous media. So later we use another model called the surface energy-based contact angle model. In this model, we don't define the contact angle explicit. Rather than we use the Young's equation we just define the three surface tension coefficients. Then the contact angle can be determined implicitly. So we did some basic tests, like we create surfaces with different roughness, and we use this contact angle model like this. We found that with the increase of roughness, like let's say from surface 1 to surface 3, we found that the contact state changes from window state to Casey state, and also the wetting area decreases. And also with the increase of the contact angle, the wetting state also changes from window state to Casey state. This is actually reasonable based on experimental observations. And then we did some other tests, like this is the infiltration process of a droplet into the porous media, let's say. And okay. And this is the physical times for this problem is around half an hour. And we can see the infiltration process of this. And also I use some irregular particle shapes. Let's say like this. Okay, this is just, we just verify because this is our recent work, so we just verify the stability of our methods. And for the accuracy, we have to verify that later. We will do some experiments or use some theoretical solutions to verify our methods. And later we will also need to consider the movement of the solid particles so that we can simulate some erosion, soil erosion or debris flows, considering the hydrophobicity of soils. Okay, then that's all for my presentation. Thanks for your attention. Okay, okay. Yeah.
Slightly change the interfacial force.
Yes, because for this model, we don't change the contact angle directly. We change the surface tension coefficients. So that will change the surface tension force.
Does that represent the interfacial force between the liquid and gas that covered the inlet?
Yes, yes.
I suppose if you want to change the contact angle, that should be related with the solid state. So interfacial force associated with the solid gas or solid liquid. Is there any reason you change instead of the solid associated constant, you just change the liquid?
Yes, we change the three surface tension coefficients.
Yeah, in theory, contact angle can be changed, but in physically, if you made using the same liquid and gas, and you only change the solid surface to change the different contact angle.
Oh, you mean just change the contact angle, or we remain the surface tension force unchanged? Okay, thank you.
Pressure gradient in the momentum equation,
Okay.
you have discretized it differently for solids and fluids. Why is that?
I mean this page?
Yeah.
This one? Yeah.
For solid and for fluid, the 1 by root grad P curve, why is it discretized differently?
Because this is because the constitutive relation for solids and fluids are different. Because for fluids here, we actually separate the pressure part and the viscous part. This is the pressure part and this is the viscous part. Well, for solids, usually we'll use the total stress to consider the pressure and the shear stress together.
Just
You mean for fluids, just the pressure part? The pressure part actually is the same with the solids. If we just consider the pressure part, this is shear stress, they are different. Okay, thank you.
So have you tried benchmarking for Laplace pressure, for example, or any dynamic benchmark in terms of the capillary flow, whether you're getting
I haven't.
dynamics or not yet?
Yeah, but I will do that later. Thank you. Yeah.
Then let's bring.
Yeah. Thank you.
This one. Straight away, or do you wait until 4:20? You upload the new one? A23. Is it the right version?
Yes.
So our second speaker for the session is Gary Marseille, and going to tell us about dynamics of liquid film over planar and topographical substrates. So Gary, please.
Okay, thank you for the introduction. So I'll be using LBM to solve thin film flow problems. Why thin films? Because they are so common in our life, and also in industrial coating, like every appliance that we use nowadays is coated with some or the other material to enhance the surface properties. And sometimes it's also used to increase the surface area so that we can have a more efficient heat exchanger. So since we'll be using lattice-Boltzmann method, let's briefly go through the basics of it. LBM is basically a mesoscopic fluid dynamics approach in which we use distribution functions in place of velocity and pressure fields. Distribution function is basically number of particles present at the location del x in the lattice velocity direction del c at the time del t. The evolution of distribution functions is governed by the Boltzmann transport equation, which is this, in which this omega represents the collision operator, which is a complex operator and needs to be approximated. I'll be using the Bhatnagar-Gross-Krug or the single relaxation time approximation, where this 1 by tau represents the relaxation frequency. This relaxation frequency is further related to macroscopic property kinematic viscosity through this CS square tau minus 1 by 2, where the CS square is further the lattice sound speed, which is used to calculate the lattice Mach number. Lattice Mach number is a very crucial parameter while dealing with LBM because it has to be less than 1 so that LBM is applicable to our problems. Next, since my problem would be a multi-phase system and I'll be dealing with very high density and viscosity ratio cases, so we used phase field lattice-Boltzmann method. In this approach, we basically solve two transport equations, one for the flow field and other one for the fluid-fluid interface. The equation that we solve for the flow field is equivalent to the continuity and Navier-Stokes equation in continuum range. However, the fluid-fluid interface Boltzmann transport equation for the fluid-fluid interface is equivalent to the Cahn-Hilliard equation. I'll be using T2Q9 lattice model to solve these transport equations. This is basically a two-dimensional lattice which has 9 directions, out of which one is the stationary direction represented by 0. And then we have nearest neighbor and next nearest neighbors whose weighting factors are calculated based on symmetry and isotropy constraints. Next, the macroscopic properties from the distribution functions can be calculated using, so this velocity can be calculated using the first moment of distribution function, and the zeroth moment of fluid-fluid interface evolution distribution function would give us the order parameter. The order parameter is used to basically describe different phases. If we are in the liquid phase, this order parameter's value would be 1, and if we are in the gaseous phase, this value of order parameter would be 0. Next, this solution is transport equations are solved in 2 steps. First one is the collision, and the second one is streaming. Solution solving this equation from here to here can also be called as collision, while transporting all the values from one lattice to its nearest lattice is known as streaming. Collision is equivalent to the viscous term in Navier-Stokes equation, while streaming is equivalent to the convective and pressure gradient term in Navier-Stokes equation. Next, after writing the code, now we need to validate this model for various benchmark cases. First, we did the phase separation, and then we validated the values of surface tension using the stationary droplet test. After this, the contact angle validation is performed using the droplet spreading on a flat surface. So on this boundary, we have used geometry-based wetting condition, whose formulation is given here. However, if we use geometry-based wetting boundary condition, we see a problem that this droplet will disappear with time. So in order to conserve mass, we have also utilized no flux condition along with the geometry-based boundary condition. The initialization for this validation is a semicircular drop with 90-degree angle would be initialized, and the simulation will be left until it achieves a final equilibrium state. And then the imposed contact angle and the equilibrium contact angle would be compared. So the maximum deviation that we got in the equilibrium and imposed contact angle is 0.035 radians. Next, now we'll be applying this framework to the falling film problem on a planar substrate. We'll be using a Newtonian fluid. This plane is inclined at an angle alpha, and because of the difference in mobility at the contact point and far away from the contact point, we see a formation of capillary ridge. Now, so this is for some theoretical part. So if we change the reference frame into a moving reference frame, which is moving with the velocity of contact point, then for some cases, we'll see a steady state problem. We'll see that this profile does not change with time. This is only for some cases. We'll be using this for validation further. Next, since we have a moving contact line problem, we chose a case where a liquid heavy mineral oil was falling onto an inclined plate, and location of contact line was reported. So we also created the same framework in Elmium and compared the location of contact point with the experimentally reported data, and it matched well, which validates that the movement of contact line is valid for this, for our model. Next, we also validated this model with the analytical results. These analytical results are calculated within the lubrication approximation. So for that case, we need to have one dimension whose length scale should be much smaller compared to the other one. And also the Reynolds number should be very small. Here, this evolution equation is derived within the slip model where lambda is the model parameter. So in order to figure out the value of lambda, we have fixed the value of mobility coefficient, which is neta is equals to 0.1, and then found out what lambda would fit with this mobility coefficient. That is for the first case, these two. So we found out that lambda is equals to 0.0013 is working for our case. Then we fixed the value of mobility and Greenspan slip coefficient and performed some more simulations by changing the value of advancing contact angle and also the inclination angle. For both the cases, we got fairly good comparison, except for the case when we have very high values of contact angles. So what happens? A lubrication approximation is valid for very small values of contact angle only, and this is a very high value. So this is also acceptable. Next, we will be now studying some of the effects which are quite difficult with the theoretical approaches, like the effect of aspect ratio. So we'll be increasing the effect of aspect ratio from 0.31 to 1 point some value. As the increase in aspect ratio is associated with the reduced influence of surface tension, and this capillary ridge is the manifestation of surface tension. So with increase in the value of epsilon, the maximum height of this ridge is decreasing. In the second graph, as we can see that with increasing epsilon, the height is decreasing and it eventually reaches 1, which means there is no capillary ridge present at this location. And the film and the maximum height stops changing. However, there is still some change happening in the flow direction. We can see a protruding structure appears, whose magnitude increases as we increase either the value of aspect ratio or if we increase the value of contact angle. Next, we also change the wettability of the surface. And based on that, we calculated the value of contact point, velocity of contact point throughout the domain. And we found that it is highly dependent on the wettability of the surface. And there is, so we expected that the maxima of velocity would be somewhere near where we have minima for the contact angle. However, as this contact angle value starts reducing, this fluid present inside this ridge becomes less and less and less. So this maxima is slightly shifted from the minima of contact angles. Next, we have also tried to solve the problem with the non-planar substrates. The height of this mount structure or the topography will increase from surface roughness to a few times film thickness. For this case also, we first performed an experimental validation case where in the literature, a S1 shape structure was present onto which a film of silicon oil was flowing. And we again created the same framework in the albium by converting the physical units into the lattice units and compared the results. Further, the analytical results calculated using the same assumptions. Here also we have some difference present at this location, which is basically because of the presence of large curvatures in the streamlines. For large curvatures also, the lubrication approximation starts to break down. Next, we increased the height from 0.3 to 1.7. For all these cases, we could get a steady state solution, but if we further increase the height, we will get into the range of unsteady profiles, which basically means the film won't be uniform, it will rupture and will lead to the periodic formation of droplets. However, and further, if we change the value of aspect ratio, so what will happen if the value of surface tension is not sufficient? This formation of nose-like structure won't have as much fluid as it has for smaller aspect ratio cases. So the drop formation will take place a little early, and we can see that frequency of droplet formation will increase. Finally, the effect of capillary number. Here we basically wanted to see how much separation is needed between two topographies so that we have independent capillary ridges. So if we decrease the value of capillary ridge, we can see a larger region of influence for curvature pressure. So the value would depend on the capillary number. And finally, the conclusion, we can say that PFLBM is a viable alternative to solve film problems. And we saw a protruding structure for high aspect ratio cases. Then surface wettability affects the film profile drastically. And also if we increase the height of topography more than a critical value, then a periodic formation of droplets will take place.
I guess in your lubrication approximation, there is essentially an idea of slip.
Yes.
I guess in our displacement, the slip probably comes from the contact lens slip. Have you ever checked that, or do you think it comes from something else?
So I use
What is your lambda parameter?
we also had this question, but eventually we got to know that if we have a diffuse interface method, then we don't really have to externally implement the slip into the model. It will automatically slip.
Yeah. So for example, you could look at the advancing angle versus velocity, and then you get an effective slip from Cox-Voigt of that law.
Yes, we, yeah. We didn't do that, but there are papers who have done that.
I know the theory.
You want to start now, or you want to wait until they're supposed to?
We can start that. Yeah.
We're a bit efficient with time, so we're still a bit early. So I think we'll just start. I hope everyone. Yeah. Okay, so the third speaker is Milo Feinberg, and he's going to tell us about transition time of the bouncing droplet. So
Thank you. So I was originally going to be presenting a paper looking at droplets bouncing into macro-textured surfaces. Unfortunately, we weren't able to wrap that up quite in time for the conference. I'm going to present some work by some of my colleagues that's on a very similar and related topic, but looking more detail exactly what's happening within the droplet and less about the interaction with the with novel surfaces. Okay, there we go. Okay, so just to get everybody on the same page, this is the basic problem that we're looking at, which is droplets landing on these surfaces. This is two different Weber number cases. So basically different amounts of energy in the droplet as it approaches the surface. And they go through basically the same set of regimes. So there's a contact point, there's a lateral spreading or radial spreading after contacting the surface, and then there's a retraction, and the energy is basically inverted, and now you have axial motion in the opposite direction. The classic thing people look at here is contact time. This is one of these important parameters that people who are interested in these kind of problems look at. And An interesting feature of this is that the contact time is not related to the Weber number, or the input energy, but actually to the inertial capillary time, which is the square root of something very similar to the mass divided by the surface tension coefficient. And people noticing this resulted in a very nice analogy to a very simple system, like the kind of canonical mass spring system. And here you have basically the same behavior. You have a square root of mass divided by a spring constant. And for the bouncing droplet, you have a square root of something related to mass, which is off by a factor of 4/3, divided by the surface tension. And the surface tension does basically function as a spring here. As the droplet spreads out, the surface area increases, and therefore the amount of energy stored in surface tension increases, and then it retracts, and then the whole system goes backwards. Today, I'm going to talk a bit more about a different characteristic time, which is the transition time. And this is the time between the impact of the droplet with the surface and when we see this reversal from radial motion back into axial motion. And you can see this happening kind of right in the middle of the slide. You see there's a little bump that kind of sticks up off the top of the droplet. And this is the formation of something called the Worthington jet, which is something that happens. It's caused by this change in energy direction. We've looked at this now with two different methods. First is experimental methods. So this is done by some colleagues of ours in China. And they've been doing these little drops, and they land on these polished copper surfaces that have been treated in all sorts of ways that I don't understand to make them super hydrophobic. And we've also then been able to go back and look at it using simulations as well. And for that, we're using the classical Shanshen pseudopotential model, which I think people are fairly well familiar with. We ran a whole bunch of different simulations. We're using the Peng-Robinson equation of state. And we looked at a range of Weber numbers and have examined what happens with the transition time. So an important question is, how do you actually measure the transition time? So, when you're talking about contact time, it's fairly clear when the droplet comes in contact with the surface, and when the droplet leaves contact with the surface. You can pick that up very easily with the camera. It's a little bit harder for transition time. The formation of this Worthington jet is what we use. And that's the formation of this little bounce. So that's how it's done in experiments. We have some other options, and because we can monitor more things when we do simulations. So we can do the same thing on the, I guess on your left, there is a plot of the kind of half height of the droplet, and we see kind of this hockey stick change that happens as the Worthington jet forms. But we can also look at other things, and the most useful one actually is this one all the way over here on the right. Which is that as the Worthington jet forms, we get very large gradients in the velocity at that spot. And so there's actually a large spike in the measurable dissipation within the droplet. And that's a very convenient way to measure kind of where this contact time or this transition time occurs. So the thing that's somewhat interesting about the transition time is that, like the contact time, it turns out to also be Weber independent. And it seems to happen at exactly half the contact time. So halfway between the droplet hitting the surface and the droplet leaving the surface is when this transition roughly happens. And it's also interesting to note that the point of maximum spreading occurs at a quarter of the contact time. So the droplet lands, it spreads out. That's a quarter of the way through the whole oscillation. It retracts. The motion starts to become vertical. That's now halfway through the transition. And then for the rest of the case, the droplet starts to lift up off the ground, as well as have kind of an axial elongation. So another thing that we did when we were looking at this is we examined kind of a mass partition of the droplet. So if you look at the droplet when it's at its maximum spreading, it has a very characteristic shape, which I will show here. So it has a thin surface in the middle called the lamella, and then on the outer rim there is the rim, and there's a kind of a mass of fluid there, and these are separated in a bunch of different ways. There's a very clear volume partition here. There's a thin neck between the lamella and the rest of the rim, and so it's very easy to make a division between the two. But there's also differences in the way that the flows are behaving and the flow regime. You basically have an expanding boundary layer in the lamella, and therefore a lot of vorticity and things going on there. And you have different behavior. You have kind of recirculation behavior at the top of the rim, and a lot of water or droplet that's just kind of going along for the ride and doesn't have very much shear in it. So they're in very different shear and flow regimes as well. So we were interested in this mass of fluid that's in the lamella. And we ran a simulation basically where we seeded our droplet with a whole bunch of massless particles at the beginning of the simulation, ran it forward, and then stopped at the point of maximum spreading, and then took the ones that were in the lamella and kind of integrated backwards in time to figure out where they started from. And this gives us kind of a region within the droplet that will eventually become the lamella. And to get a nicer picture of what's going on here, we reran that simulation, this time using an interface tracking algorithm. So we used that initial surface that we had generated and used an Allen-Kahn equation basically to track this interface within the droplet. So the droplet dynamics are still entirely Navier-Stokes, but we have this Allen-Kahn solver that's running in parallel and just tracking kind of how this surface evolves over the course of the simulation. You can see kind of what the results are here. We have this it starts kind of in the top half of the droplet, and then it spreads out. We get the lamella, and then it ends up at the bottom half of the droplet as the droplet takes off again. But something that's very interesting about this is that this partition has the same ratio between lamella and rim, or future lamella and rim at the beginning of the simulation. Basically, again, it's consistent with Weber number. And the volume that's in the rim is 3/4 of the total volume of the droplet, and the volume that's in the lamella is 1/4 of the total droplet. So yeah, so here you can see some experiments and simulation data plotted against Weber number, showing the ratio between the total droplet, the volume of the rim and the volume of the total droplet. And this actually ends up being kind of a nice extension of this very simplified mass spring analogy that I mentioned at the beginning. So here's the inertial capillary time for the lamella droplet alone, and that's because we have 1/4 of the volume. It basically comes up to having half the characteristic time, and that's what we see. We measure when we measure half the characteristic time for this transition time as well. And so what this sort of implies is that there's kind of two different. Well, there's an oscillation happening with kind of two modes. So you have an oscillation that lands, and then you have these kind of two different modes of oscillation as it retracts. So yes, some conclusions. There is a transition event. We can detect it by the formation of the Worthington jet and by the dissipation that's caused by this flow formation. The transition time is independent of the impact kinetic energy or the Weber number, and is also scales with the inertial capillary time, as does the contact time. The transition time is roughly half the contact time. The maximum spreading time accounts for 1/4 of the contact time. And if we do this volume partitioning, we find that there is a characteristic volume of the lamella, which corresponds to this transition time as well. So they have the same characteristic time associated with this characteristic volume. So yes, at maximum spreading, the lamella accounts for 1/4 of the droplet volume, and the transition time is kind of the halfway point in this full oscillation that the droplet undergoes. So that's the presentation. Full details of this will be published hopefully shortly. So I direct anybody who's really curious for more details to this paper.
Is the reason why I should consider time not one contact time?
I'm sorry, say that again? Yes. Yes, yeah, I mean, they're related to each other. I think it's not that one replaces the other, right? Like the contact time is a characteristic time of how this droplet behaves, but there is a second, there's a large scale oscillation that happens in terms of the droplet landing, spreading, and coming back up, right? But there is also a secondary oscillation that's happening, which is the droplet basically spreading radially and spreading axially. And that has a different characteristic time, which is the transition time. Yes.
You have the tool, so if you change some parameter which could affect the y-axis value. So, for example, not using the weapon for example, change the contact with something and see how the transition time change. I think that kind of things could be finding something disconsistency. You already know that we're not changing.
So I think like these kind of mass spring analogy models, they give you some indication that there is going to be something like a transition time there to find. And then people go with the simulations and with the experimental validation, basically to try and make sure that these models are actually fitting the droplets that we were designing them for. So.
This is a study performed in the context of a certain type of setting. So people usually look at program dependence of droplet impact the surface or superhydraulic surface. And this is a study in that context. So that's why we observe a modeling area surfaces, and we see that it's also
so you change the hydrophilic filtering in the simulation.
Yeah, but that also affects the context.
What kind of forcing scheme can be introduced in simulation?
In the lattice Boltzmann simulations. So we're using the Shan-Chen pseudopotential method. The forcing scheme. Yes. We're using Kupperstock, yes, which is our exact difference method.
DROPLET. What is the advantages of using an EDM scheme?
Well, I mean, there's various different ones out there. I only personally have experience using EDM. One nice thing about it is that if your force is constant over the course of the time step, it is exact. So if your time steps are relatively small, in theory, it should be fairly accurate. Yeah.
So in the past 5-10 years, I think there's quite a bit of industry in trying to minimize contact, and people have started looking at codes.
Yes, all sorts of macro textures and
So
things like this.
are you trying to argue that this idea of transition time versus contact is the same? So this is that's something invented.
No, I think that would be an interesting thing to look at. I assume that there are probably so what is similar is that this idea of partitioning, that's something that maybe actually in some ways comes originally from this literature looking at other kinds of surfaces. So there are simulations where they have or studies where they have droplets landing on little point surfaces or things like that. And the way that they analyze these is they find they basically break them into different, either into multiple volumes that they can then look at the expansion and retraction of independently, or sometimes like if you have it land on a small point, you end up with a ring droplet that happens. So your lamella gets punctured in the middle, and now as things contract, you now have a different contraction length, which you can associate with a different contraction volume. So this is maybe in some ways taking concepts that have come from that and then reapplying them to the original pancake bouncing problem to find more interesting details about how this physics works.
Well, let's thank the speaker and let's thank the audience.
Good talk.
At the end of today's session.